Hello and welcome to the presentation of the Advanced Process Optimizer, or APO. We believe that all other things being equal, the simplest solution is the best one, and we try to act according to that principle in optimizing an industrial plant, which is what APO is there to do. At the present moment, most industrial plants are being operated and controlled by human beings that base their decisions upon their own experience and their training. In that, they look at a few key variables that they've discovered from their own experience and use that data to support their decisions on what modifications to make and the set points of that plant. They cannot possibly look at all the data that's available from the plant because there are thousands upon thousands of measurements that are present, and also each one of these measurements is renewed every few seconds. So the sheer volume of available data is far too much for any human being to look at or understand. Additionally, significant data, especially from the financial markets outside, is simply not available to the operators at the time of making their decisions, and so they cannot take some information into account in making their decisions. Operators, as human beings, operate in shifts because they need to go back home to eat and rest, and so the operators do not control the plant continuously 24 hours a day, 7 days a week. In fact, they operate in shifts. And what you will experience if you're in the control room at shift change is that the next team always believes that it is better than the team it is replacing. And it has a different experience, a different training, and different opinions. And therefore, the team, as it enters the control room, will make some dramatic changes right away in order to get to what they believe is the better condition. As most industry plants need quite some time to react to new set points, that transitory motion to get to the new points makes it take some time, and therefore the plant is rarely ever in the optimal condition. This is, of course, repeated at the next shift change. So operators make good decisions, but they do not make optimal decisions. And in the various shift teams that you have, one team is the best and the others are not the best. All that means is that your plant is hardly ever in the optimal condition, but it could be if you analyze the data in a different way. We would like to be at the optimal condition at all times, and for that we need to look at every piece of data available in the plant, and we need to do it continuously all the time. Instead of being based on experience and training and different people's personal opinions, decisions must be based on objective evidence that does not change over shifts and that does not change over time. Also, the operational execution mustn't be limited to a shift, but it must be a 24-hour-a-day, 7-day-a-week initiative that remains continuous across shifts and across months. A human being cannot possibly do that, so we need a computational optimization which is based on a mathematical model that encapsulates the dynamics of that industry plant. Here's an example. The diagram you're looking at has 3 dimensions. The horizontal dimension from left to right, as well as the dimension into the board, are 2 set points that a human operator can control in a particular chemical plant. The vertical axis in the diagram is the result of those actions, which in this case is the chemical selectivity. Selectivity is something that we like to be large, so the tops of these mountains that you see are good points, and the bottoms of the valleys that you see are bad points. So we like to stay at the top of the mountain range And in seeking the optimal point, what we seek is the peak of the largest mountain. So we've performed an experiment on a real chemical plant that is drawn in this image here. We started off at the point on the left-hand side labeled starting point, and we gave the human operator the task to bring the plant to what he believed was the optimal point. He took that gray path to get from the left-hand side to the right-hand side of the image, and at the end of the gray path on the right-hand side, he stopped and said, "This is what I believe to be the optimal point." We took the plant back to the starting point and gave the same task to the computer algorithm. The algorithm chose the green path and ended up at the right-hand side at the point that's labeled optimal point. The difference between the two endpoints is 5% greater selectivity, and also during that transition, aggregated over that time from left-hand to right-hand side of the image, which in both cases took approximately 8 hours to do, is also 5% greater. So we can see human experience and knowledge is very good. It's only 5% away from the optimum. On the other hand, those 5% can actually be obtained in a realistic production plant if a computer algorithm trained on empirical data is used to achieve it. So you can optimize the plant's performance, in this case chemical selectivity, but you might as well have chosen yield or even a financial figure such as profit to optimize. And in our experience, something like 5% or even 8% is in fact realistic in real-life plants. The mathematical model that is behind this is in the form of a recurrent neural network, where the word recurrent means that this is a time-based model that incorporates cause and effect relationships over several time scales from seconds to hours, days, and weeks, so that cause and effect relationships that might take quite some time to manifest are incorporated into seeking how to get from the current point to the optimal point in the best way possible. And these models are trained automatically by a machine learning algorithm in such a way that the human engineers do not have to participate or prescribe any kind of experiential knowledge or physical knowledge. This model can be trained in a very short space of time. In just a few hours, the model can be ready. Here are a few examples of this. Here's a silicone production plant that was modeled in this way, and it was found that by changing the amount of catalyst elements and promoter elements in the chemical reaction, the selectivity could be increased by 3%, and at the same time, the yield of the reaction could be improved by 5%. Nonetheless, we had to compensate for environmental factors such as the air temperature and air humidity by modifying pressures and temperatures of the process. So we had a slew of set points available to be changed in order to optimize selectivity and yield. And you can see in the diagrams on the right-hand side, this is the distribution of values for the selectivity on top and the yield at the bottom. The dotted red curve is before any optimization, so this is human operator doing, and the green curve is after the optimization has been applied, where that blue dashed curve is the intermediate transitionary period where the optimization algorithm was being introduced and therefore in partial usage. And what you observe is that in both diagrams, the average value moves to the right-hand side. That's the increase in average performance. But what you will also note is that the width of that distribution is reduced, which means that the process becomes more and more stable over time as the optimization is being more and more used by the operators of the plant. So you get a more stable and more performant process simply by introducing a computer suggestion system for changing the set points. Another example included an oil platform offshore in China, which had access to a large number of wells. All these wells, however, were in the same reservoir under the same ocean current, and so these wells are not independent of each other, but rather they interact. And so placing load on one well takes away load from its neighbor. And therefore, we cannot just increase load on all the wells, but we have to carefully balance the load between wells in order to increase overall yield. And so, compensating for the reservoir and the weather as well as the ocean, we can bring about a load balancing between the wells and in aggregate improve the yield by about 7%. The same thing can be done in a chemical plant environment where we might have, as in this case, 7 different chemical reactors of different design run with different catalysts but hooked up to a common feed system and producing the same chemical. Here, we also want to load balance between them and optimize the overall system to again improve selectivity and yield. And here again, we can observe significant increases, 3% selectivity, 4% in yield, just by controlling how much load each reactor takes. In power generation, we might want to improve the overall efficiency of a power plant. And in this case, we have a CHP plant that produces both power and district heating. And we were given control over the set points only for district heating. The power generation was automated fully already. We were able to modify the set points for district heating, but we had to respond to the boundary conditions of the electricity demand, the weather, and the fuel markets, as well as, of course, the demand on district heating, which is, of course, mainly dependent upon the air temperature. Overall, we were able to achieve a 1.1 overall power plant efficiency gain just by changing the district heating. And that's very significant for a power plant. A different power plant example is looking at the internal demand. So a power plant itself needs some electricity to run itself. And that internal demand for electricity was our goal here. We were allowed to switch on and off several pumps, mostly for cooling water, and fans in the cooling tower. We were given the opportunity to turn these machines off when they were not necessary. And we found that overall, we were able to reduce the internal electricity needs by 9%, which of course enabled the power plant to sell those 9% of electricity on the free market and thereby increasing its revenue. Of course, doing this, we had to obey several boundary conditions which were related mostly to weather, of course, because both the cooling water pumps and the cooling tower fans were related to cooling the power plant, and of course the production capacity, the amount of steam, pressurized air, and electricity that was demanded by the load balancer. That was not up to us to control, so we had to respond to that boundary condition as well. Another example is a completely different kind of plant. It's an air separation facility which takes in air from the atmosphere and separates it into its various chemical elements. And here we want to reduce again the amount of electricity that the air separation facility uses. And we control that machine with a number of set points, and we're able to reduce the overall energy demand by 4% while keeping constant the actual operational yield of that air separator in its various components. In summary, the machine learning method that computes a mathematical dynamic model from empirical data in a process is able to find the optimal point and get to the optimal point objectively, continuously, in real time, over the long term, by looking objectively at every piece of data available from that plant and to suggest real and concrete actions to be taken by the operators in order to boost that performance. And performance could be a physical or a financial quantity, and we've seen improvements of up to 8%. And what you see in the diagram above is that not only does performance improve, that is, the mean of the distribution shifts to the right, but also the distributions get tighter, so at the same time the process becomes more stable. I would like to invite you to try out APO in your plant. No technical or mathematical expertise is necessary for this. It takes only minimal effort to install the software, and the software can be up and running in just a few days. Try out the technology in your plant, make a proof of concept over there, and see for yourself that this is truly realistic and can, with little effort, reap enormous rewards. This is our customer support team, and we would be happy to receive your questions and comments. Contact us here, and you might also want to read the book Optimization for Industrial Problems that I published some years ago, which will give you all the mathematical background as well as the project management history of this, and 19 real-life case studies with their industry contacts in it to see that we have done similar things for plants just like yours. Thank you very much for your attention.